Cool. Is it recording? There we go. Cool. Um, Share screen. Start broadcast. Can you see my screen? I said there's like 20 people. There's like 2 of y'all. You can hear it? You can see it? Yep. See it? Cool. All right. Well, I guess we're going to get started. It's 11 a.m. I'm going to just double check if there's anybody. Oh, there we go. Okay. Well, no one else is in here. Being recorded, whatever. All right. So I've prepared 6 problems for y'all. In your problem sets, you've had 5 subtopics. You've had like a different, you're deriving the differential equation and finding your omega n and finding your zeta. You've had the network parameters, which are whatever it's called, driving point, no, not driving, like trans impedance or whatever. You've also had, what was that last part? Open circuit and short circuit natural frequencies. That's one of the fifth, or one of the third on your problem sets. Your second problem set so far has been Thevenins and Nortons and oscillators. Has he talked much about oscillators in class? You just finished it. Okay, cool. And y'all's problem set is due Friday. All right, cool. Well, like I said, I have 6 problems. I have one for every subtopic. Plus, for Thevenins and Nortons, I have one of each. If y'all are probably fine on that, we can just keep that, or we can keep it down to 1 if y'all want. But yeah, cool. Well, let's get started. So I'm gonna read the problem. The voltage-driven network shown in Figure 1 is operating in zero state conditions. That is, the inductor and capacitor have 0 initial conditions. Using the components shown in the schematic, you are asked to do the following. Derive the time domain ordinary differential equation for the capacitor current I3 of t. Express the ODE in the usual form of what's shown. Express coefficients AI and Bj in numerical form. And then part B is calculate the values for undamped natural frequencies omega. I'm sorry. That is omega, right? Omega n? Yep, that's omega. And the dampening ratio zeta. Describe the nature of the response, overdamped, critically damped, underdamped, or oscillatory. Show the work, whatever. All right, what do you think we need to do first? Oh, if anybody wants to take a photo of this, you're more than welcome to. Kind of just have it down. You said MAME. I'm very curious if there's anybody in the online. Let's see. Nope. Yeah, whatever. Okay. Yes. So you said MAME. Do you agree? Sweet. Okay. So I'm going to put my arrows like this. That's really bad. There we go. Okay. Also, my handwriting is atrocious. Need clarifications? Let me know. There more people coming? Wow, that's crazy. How's it going? I'm basically just getting started. I got about 6 problems to go for, so I'm doing one of every subtopics, and I got a Thevenins and a Nortons. So this is, what's up? This is being recorded in the HKN Teams, in the UTA EE Discord under the Circuits 2 channel. I linked the channel. I linked the Teams for HKN. Yeah, so this problem is basically the first subtopic on your problem set 2 or problem set 1. If you'd like to take a photo, you're more welcome to. How to get started. Basically, I'm using MAME, and I'm going to be trying to do part A and part B as described. So, MAME, we're just going to do MAME. Can I unlock this thing? There we go. Okay, so MAME, okay. Well, so what is everything? Okay, MAME uses what? What? Well, like what components are in MAME? Like you have voltage sources, current sources, resistances, conductances. What do you use in MAME? You said voltage sources, yes. And then in terms of resistance or conductance, what would you use? I agree. So we have to use the resistance and the resistance. I'm sorry. And speaking of resistance, the full thing in resistance is impedance, right? So we then have to use the impedance of this inductor and this capacitor. Okay. So I'm going to just basically do the MAME real quick. So SL1 plus R2, right? That's in the top left. What's being shared between the 2 meshes? What component? Yep, R2. So that will be negative. there and negative there. All right. Yep.
The SL1, I've like seen that. Is it just a chart that we have on material?
Yeah, that's just the impedance of an inductor.
So it'll always be that.
Correct, the impedance, but the admittance is what in terms of admittance is what to impedance.
Gotcha.
Exactly. So for if the impedance of an inductor is one SL, what is the admittance? No. Just take the inverse of that SL. What's the inverse of SL technically over 1? What's the inverse of that? 1 over SL. Yeah. So, all right. And then for mesh 2, R2 plus 1 over SC3. I was telling them my handwriting is atrocious. If you have any questions, literally let me know. So then these are all multiplied by your IM1 and IM2s. All right. And now we go with our voltage sources. What's connected to mesh 1? EG? Is it going to be positive or negative? I agree. All right. Is there anything else that is connected to that? I agree. All right. And we have a source in mesh 2. Is it going to be negative or positive? Everybody else agree? I agree as well. RM I2 of S. All right. Well, we need I2 of S to be in mesh currents. What is I2 of S? And I agree. All right. I'm just going to take the source matrix and transform that. So that will become, I want to separate it into our independent. That's not supposed to be a 0. That's supposed to be a S. Independent and dependent. So like we said, 0 RM times IM1 minus IN2 right there, right? So what do we do now in terms of transforming that matrix? Well, we still have one technically it's a vector. We have one vector that still have your mesh currents in it, right? So what's the next step to get from what do we do with that one vector with the mesh current still in it? What would you recommend we do? Into what? Yep. So this one then becomes 0 and 0, right? And the thing multiplied by IM1 would just be RM. And the thing being multiplied by IM2 is what? Boom. All right. And that's all being multiplied by IM1 and IM2. What do we do with this matrix? Bingo. So I'm going to so what is that? That is SL1 plus R2. And there's nothing going to be changing in the top because it's zeros over here. And then negative R2. All right. Then we have a negative R2 over here. And since we're subtracting a positive RM, that is also being subtracted in this new matrix. And then we also have the R2 plus 1 over SC3, and we're subtracting a negative, so that's going to be a plus RM. That's all multiplied by IM1, IM2, which equals EG of S. All right. What do we do next? So we are looking for the ODE for I3. Does that make sense? So what is I3? We're using MAME. MAME uses mesh currents. So we want to transform that I3 into mesh currents. So what is, I agree. So I3 of S equals IM2 of S. Does everybody see why I3 is IM2? And it's exactly. If it was going the opposite direction, it'd be exactly.
What if it were like in between? Could it be like IM2?
Yes. It could 100% be that. Yeah. For this type of problem, I would be shocked if he does that. It's going to make everything a lot more difficult, but you can do it. So now what do we do next? There's a certain rule with matrices that you can do. Kramers, right? So Kramers, right? We're using mesh 2. So can someone explain to me what how I get the Kramer equation? I don't know. Yep. Yep. Oh, you go. Well, this is the technical way to say Kramer's. I didn't mean that far, but basically, you take you have a -1 there. Okay, you take oh shoot. So you are looking at your second mesh, right? And you have an independent source in your first mesh. Okay. Because of that, we have a 1 plus 2 as the exponent. Does this make any sense? Have y'all seen Russell do this? Yes? I got you. So we're looking for a current in mesh 2. Okay. We have a source, an independent source in mesh 1. Because of that, we have a reference of 1, but we're looking at 2. So we have the reference of 1 and we're looking at 2. If it were a mesh current, if we were looking for a current right there, our reference is mesh 1 and we're looking for a mesh current in mesh 1. Exactly. And if we had a source here and we were looking for a current source here, it'd be our reference is 2 and our source is in 1. And if they were both in mesh 2, 2 plus 2. So that is how I've come to understand it. If you have any other questions on that, let me know. I can do a little bit more digging on that, but I believe so. We have a current source. Oh, I'm sorry. We are looking for a current in mesh 2. You agree with that? Okay. We are referring back to our independent source, which is in what mesh? Exactly. So our reference is mesh 1, and we're looking for a current in mesh 2. Does that make sense? Because the actual form of Kramer's is, I'm just going to do this, equals -1 I plus j times delta I times j over delta times whatever. Well, I'll do that right now. And your I and j's are what we're talking about. Your I in this case is that reference you're looking at, which is in mesh. If our reference is that source, our reference is in what mesh? The independent source, I'm sorry. Exactly. So that's our reference, 1. And our second, or what we're actually looking for, is in what mesh? Exactly. So reference is I, what we're looking for is J. So that's why we get this 1, 2. And I was explaining if your source and your current was in mesh 1, we'd just be looking for mesh 1. If it was just, if your source and if your independent source in your current was in mesh 2, you'd just be looking for 2. And it kind of not reverse, but it's similar for name to where if you had a source touching one node, right? We're going to call this node 1, right? This is supposed to be current source, whatever. And you had a component and you're looking for the voltage across this. Would it be voltage? Yeah, let's just say voltage, right? That's V1, positive V1, right? So if you were to do Kramer's, it'd be -1 to the 1 plus 1 because our reference is in 1 and our voltage is in 1, as in we're looking at node 1 and then delta 1, 1 over delta. That kind of makes sense? I'm going to erase this real quick, but I hope that helps. If you have any more explanation on that, I believe I explained that correctly, but as far as I've seen, that's how I've done it like every single time. So yeah. So because of that as well, this becomes then delta 1, 2 over delta times EG of S, which just becomes negative delta 1, 2 over delta times EG of S. Y'all agree? Cool. All right. So what is negative delta 1, 1? Can anybody explain to me how we find the delta 1, 1 or delta 1 or delta 1, 2, delta 1, 1 or whatever? For this case, it's delta 1, 2. How would we solve that or find it? I got you. Okay. So we have a 1, we got a 2. The first one is whatever row you cancel out. I'm putting in that in parentheses. And the second number is whatever you cancel out in your columns. So we have delta 1, 2. So we cross out the first row and we cross out the second column, and whatever is left is your delta 1, 2. So if it was delta 1, 1, first row, first column, that's what we have to do. If it was delta 2, 2, boom, boom, that's what we got. So since we have delta 1, 2, first row, second column, that's what we use. Did that make sense? Say that one more time. Yeah, that's a good way to put it. Yeah, it's kind of it's the opposite diagonal. I like to say it's the crossing out of the rows and the columns because that's kind of easier to represent. But I get what you're saying in terms of it's kind of the opposite diagonal. So that's a good way to look at it as well. So because of that, and it's also a negative, we take this, we take this negative R2 negative RM, multiply it by that negative. So then we just get an R2 plus RM. We agree with that? Okay. I was asking them earlier on how y'all find determinants. How do y'all find determinants? Like when you're doing your computations, are you putting it in a calculator? Or are you doing it by hand? A little bit of both? What's up? You do it by hand? You do it by hand as well? You by hand? Yep. So when I do it by algebra or whatever. Would y'all like me to do that algebra, or would you like me to just show you what the determinant is? Do it algebraically? Okay. Let's do it. So delta, also if I'm going too fast, let me know. But yeah. All right. So delta or determinant is going to be this, or that would be element 1, 1 and element 2, 2. Or that multiplication of them. So element 1, 1 times element 2, 2, right? Minus element 1, 2 times element 2, 1. So it's this times this minus this times this. Is that a good way to? Yeah. Okay. So, like I said, my handwriting is trash. Please let me know if you cannot understand. S1, SL1 plus R2 times that R2 plus 1 over SC3. What is that? A plus RM minus negative R2 times negative R2 minus RM. Okay. So do we agree with how I got there based on this matrix here? Y'all agree? Wait. So now we do the algebra. So I do it a little bit, everybody does it do it a little bit differently. But I'm just gonna do it the way I do it. So I basically go from here to here. That's SL1 times R2 plus this to this. SL1 over SC3. I don't like to cancel out the S's. It makes it easier in later math. That's my personal preference. If y'all cancel out the S's, go for it. All right. And now I go from here to here. So that becomes plus SL1 RM. Okay. We're done with that first one. Now I go from here to here, which is plus R2 squared plus R2 over SC3 plus RM R2. Okay. So I am done with that. Y'all agree? Do y'all agree with how I got everything? Cool. All right. Now we do a minus, and I do a whole different fraction. So I have an R2 and an R2, so R2 squared. And that's a negative times a negative, so it's positive. And I have negative R2, negative RM, so that becomes RM R2. And as you can see, I have terms that are similar in both instances. So I have an R2 over here, and I also have a negative R2 when I distribute this negative out. So that also cancels out. Same thing with this RM R2. Those are canceled out. I'm left with my determinant of SL1 R2 plus SL1 over SC3 plus SL1 RM plus, oh, that's a weird RM. There we go. Plus R2 over SC3. Do y'all agree? That's what I got. All right. Now, I'm going to combine everything. I3 of S equals that delta 1, 1, which we found earlier, to just be R2 plus RM. So that just becomes R2 plus RM. And then our determinant becomes SL1 R2 plus SL1 SL3 plus SL1 RM plus R2 SC3 times EG of S. So another thing about calculations, you see I have in the numerator, I just have two different terms. Would y'all agree that I only have two different terms in my numerator? And then in my denominator, I have four. Okay. The biggest thing with these computations that Russell, I feel like, at least my semester, very emphasized heavily, is we do not want a fraction as a term. Especially, we don't want an S in a denominator of a fraction. Especially that. If it's a numerical number where it's like 1 over R times S, so I should say S times 1 over R, that's fine. But if we have a term that's an L over S, you're not going to get that. But an S in the denominator is something we don't want. Okay. So I have terms that have SC3. Okay. So to cancel out those, I can just multiply by 1, or also multiply by SC3 over SC3. Y'all see how I did that? Yes? No? Yeah, cool. All right. So then that just becomes I3 of S equals SC3 times R2 plus RM over S squared L1 C3 R2, because I multiply this term and that term. And then I have, since I'm multiplying this, oh, okay, I'm multiplying this term and this term, the SC3s cancel out, and I just have an SL1. And so the same thing here, SL1 C3, oh, that's an S squared, sorry, RM plus R2, all times EG of S. Do we agree? Cool. Yeah, that's what I got. All right, so then I like to combine like terms. Why did I? Let's call I. There we go. 3 of S. See, and still the same up top. Okay. So now I'm going to group it into S squareds. Okay. Well, I guess I can take those out. So L1 C3, because all my S squared terms have an L1 and a C3. So then that just becomes R2 plus RM plus an SL1 plus R2, all multiplied by EG of S. Are we in agreement? You see how I got from here to here? I just took this term and this term, factored out the S squared L1 C3 because they're in both terms, and then I'm left with an R1 plus an R4. I mean RM, R2 plus RM. Sorry if I misspeak. Let me know if you need clarification. But does that make sense to everybody else so far? Cool. What did I do now? What I like to do is put in my numbers. So if we go back to, someone say anything? Okay. If I go back to here, I see that my L1 value is 47 microhenries. My R2 value is 100. My C3 value and my C3 value is 10 nanofarads. Okay. So putting in those numbers, I'm just going to go straight to what I got when I put them in the calculator. I got an I3S equals an S times 11 times 10 to the negative 6th on top. I got an S squared times 517 times 10 to the negative 12 plus S times 47 times 10 to the negative 6th and plus 100. It wasn't it? Yeah, it was 100. All times EG of S. Okay. Another thing I like to do is we want for this class and a class called control systems, it is important to, when you have multiple terms, and I shouldn't say that. In your numerator and your denominator, it is important to have your highest form of S just by itself. So we want to get to where this S squared is by itself, and we want to get to where this S is also by itself. Okay. Have y'all ever seen the form of 8 times N over D? As Russell talked about that, we want to get this equation here into that. And that's just important for like almost all of this computation, almost basically all of it. So we want to get that into this form, okay? So I want to get a factor term and I want to get a numerator and denominator. And how we get that factor term, as in, or I shouldn't say factor, but a constant of that k, we factor out all the terms that are being multiplied by our highest form of s's in the numerator and the denominator. Does that make sense? Okay, cool. So I'm going to do that now. So my I3 of s, I'm going to factor out those highest forms of s's on both numerator and denominator. So I factored those out. So everything that's left on the numerator is just s. Okay. S squared is left on the numerator. So I factored out this number. Okay. What do I have to do to this number to get my mathematically correct number that is multiplied by s? Did that make sense? What do I have to do? Do I have to multiply? Do I have to divide? Do I have to add? Do I have to subtract? To get, I pulled out this number. I factored it out, basically making this essentially 1. What do I have to do to this number? To make this number 1, I put that number over, or I put the 517 over a 517. So what would I have to do to the 47 times 10 to the negative 6th with that 517 number? Exactly, I divide it. So when I divide this number by the 517 times 10 to the negative 12th, I get an s times a 90.909 times 10 to the third. Okay. And so I divided that number. And so it works out to where if I were to factor this back in, I just simply multiply that number, and I would get that number. You can do the math if you want to. It proves it. So I have to do the exact same thing. I have this 100 here, and I have factored out this 517 times 10 to the negative 12th. So I have to divide the 100 by that 517. And when I do that, I get this number here. 193.424 times 10 to the 9th. All multiplied by E. Okay. I guess I'm going to get that a little bit closer. EG of S. Does that make sense? Does that make sense so far? Everybody? Cool. All right. So then I'm going to rewrite this, but in this number, that's not supposed to be a 3. That's supposed to be a 3. Okay. There we go. When taking this fraction, I get a number of this. 21.277 times 10 to the third, and that is all being multiplied by s over s squared plus s times 90.909 times 10 to the third plus 193.424 times 10 to the 9th. Still all multiplied by EG of S. All right. So y'all have that written? I'm gonna go back up to the top. Okay. So we have that form that y'all just saw. And we need to get it into this form. It's where we have currents on the left and our voltages on the right. And we have different coefficients and we have differentials. Oh, also, we're currently working with S's, but we need to get differentials. So how do we do that? Laplace transform. And when you do that, what does our S's turn into? Our S are like, exactly. So every S will be a derivative. So if we just have a single S, it's a derivative. If you have an S squared, second derivative. If you have an S cubed, it'd be a third derivative. Does that make sense? Okay. Because of this, I want to get, like I said, I want to get this just one giant number. And currently I have my current on the left equals a fraction times my voltage. Well, I'm going to just multiply my numerator or my denominator. I'm basically just going to go, whoop, that's a bad arrow. I'm going like that. So then that becomes I3 of S times S squared plus S times 90.909 times 10 to the third plus 193.424 times 10 to the 9th. And that equals 21.277 times 10 to the third times S times EG of S. Do y'all agree? We're in agreement? Cool. All right. Now I'm going to factor out that I3 of S. And I'm going to do it to where it's in a similar form as this equation here. Do it into a similar form. So that becomes then S squared times I3 of S plus 90.909 times 10 to the third times S times I3 of S plus 193.424 times 10 to the ninth times I3 of S equals 21.277 times 10 to the third times S times EG of S. All right. Now earlier we talked about Laplace transform. So what do I do now? I have S's, I need to get to derivatives, and we talked about all my S's are derivatives basically. So I'm going to make my S's now derivatives. So I have an S squared. What does that turn into? Correct. Second derivative. So D squared or D2 or DT2 times I3 of T plus 90.909 times 10 to the third times D dt times, I'm going to lowercase that, I3 of T plus 193.424 times 10 to the 9 times I3 of T equals 21.277 times 10 to the third D dt of EG of T. Does that look like, does this form look like this form here? Do you notice any differences in the amount of terms? Where? Exactly. So if we don't have that term, that simply means B1 is what? Exactly. So our B1 is 0. Okay. So that is part A. That is the entirety of part A. We have our form. I will wait in just a second so y'all can write that down. I'm going to take a drink of water. By the way, we got this room for 3 hours. If we finish early, perfectly fine with me. If you have any questions for me, I'll be hanging around the IEEE room. Yeah. Everything's making sense so far, relatively straightforward. Okay. The biggest thing about the test is 3 questions in 50 minutes. But if y'all can, try to get here like 10 to 20 minutes early, because at least for my semester, I don't know if he'll do it for your first test, but he let us start the test a few minutes early. So instead of starting at 9, we started like 8:40. I was never there at that time. Got there at 9. But if I were you, I would recommend you getting there a little bit earlier, if you'd like a little bit more time. I would talk to Russell and be like, hey, I've heard in previous semesters you've let them take the test before 9. Can we do that as well? And he'll most likely say sure. So where is circuits 2 this semester? Like what room, what building? Making that guy walk. He's got circuits 1 and circuits 2 in there. Oh, that makes sense. Every morning in thermal, I see him just walk by. So, all right, cool. So now we have part 2 to do. And part 2 is okay, I don't want that. What is part 2 telling us to do? I can do that. What's part 2 telling us to do? Frequency damping ratio. All right. How do we do that? There are formulas that have been given. Start with omega. What is the formula to find omega? That's oscillators. You're thinking ahead. We have terms with different coefficients, right? We have this here. I'm gonna say this here. This equation here is like saying this. S squared plus A2S plus A1. Does that make sense? Y'all have seen that form before? Well, and then we just basically took the derivative, so it would be the same thing, but derivatives where the S's are. So through this helps us find omega in. but do any of y'all know the formula to find omega n in terms of these coefficients of your? Not exactly. It's in the square root of A1. And using this form here, what is A1? Is it here, here, or here? Last one? Okay. Yep, I agree. So that means omega n equals square root of 193.424 times 10 to the 9th. Okay. So when you do that, omega n becomes 439.799 kilo. What is the units? I agree. Boom. And that's the answer for the first part. Do any of y'all know the equation to find your damping ratio, aka zeta, which is not how you write zeta, it's just a curly z. It deals with those same coefficients. Probably in your notes somewhere. I mean, I'll just give it to you. Like, it's relatively. Just know where these things are, because he's 100%. I shouldn't say 100%. It is highly likely that he will assign one of these questions for y'all, because he has done it for the last 2 semesters. Probably. But zeta equals A2 over 2 square root of A1. What's the square root of A1? Exactly. A square root of A1 is omega n. So that just becomes A2 over 2 times omega n. And when you what is A2 as well in this equation? Is it this, or this? Second one. So that then becomes 90.909 times 10 to the 3rd over 2 times 439.722 times, nope, not 722, 799. 799 times 10 to the 3rd. And when you put that in the calculator, you find that it becomes 0.103. Can anybody tell me, well, we found 2 of the 3 conditions we need to find in part B. It says, describe the nature of the response, i.e. overdamped, critically damped, underdamped, or oscillatory. So what is this zeta? Out of those 4 terms, like I said, oscillatory, underdamped, critically damped, or overdamped. What is underdamped? Why do you say that? Bingo. I agree. I'm just going to write this out for everybody, and this is definitely important to write down somewhere. When zeta equals 0, it is undamped, also known as what he said in the problem statement, oscillatory. Okay. When zeta is between 0 and 1, not equals to 1 or equals to 0, but in between that interval, it is underdamped. Okay. All right. Third one, if zeta is equal to 1, it is critically damped. Okay. And the last scenario is when zeta is over 1. Okay, I need to write that better. Boom, boom. There we go. That's even worse. Whatever. Over damped. And do you understand what he means when he says undamped, underdamped, critically damped, and overdamped? Is that okay? So this circuit is kind of it's going to have a response. That's when you put a signal into it, it's going to have something that happens. Okay. When you look at these signals graphically, you'll have something like this. Okay, it's a rough drawing. Basically, this dampening tells you how close it's going to look to that. And so if it's undamped, wait, nope. I'm sorry. Wrong part. Yeah, come on, wrong one. Okay. You're going to have a signal that comes in. Okay. And various different signals, various different circuits are going to produce different things. So if it's undamped, it's just basically going to go like this and be oscillatory and oscillate. If you were to have something that's underdamped, it's going to do that same thing, but just slower. If you had it critically damped, it's basically going to be a straight line. And if you have it overdamped, I honestly don't know what happens when it's overdamped. But basically, the signal, the dampening ratio tells you how stable that circuit is. And we have it as undamped. So that means our circuit is what? I would agree.
Does that mean ideally if you want like
If you want something that, if you want a circuit that will be stable and have like a straight line and no ripples or anything like that, yes. But in certain scenarios, you might want something that's underdamped. You might want something that's an oscillatory circuit. I kind of don't think there's going to be any time you want something to be overdamped, but I could be wrong. So does that make sense? Was this process relatively straightforward? Cool. All right. Move on to the next question. Yes. Which equation? The very top? Okay, gotcha. That's our omega in. So no, it's simply this type of question. This is the problem statement. This is the circuit is just going to be different. Like on your first problem set, I think your first two questions were very similar to this. And like I said, the last 2 semesters, he has assigned one of these questions on the tests. What else? And just remember, omega n equals square root of A1. And remember what that is in terms of the equation. This is the equation right here. So A1 is the square root of that term. And then zeta is that A2 times 2 square root of a square root of n, which is also square root of A1, sorry, which is also just saying 2 times omega n on the denominator, which gives you then your damping ratio. So these equations are what you need to know for sure, because that's just something that Russell teaches you, and you can derive everything else. Like you saw, we derived everything else. Okay. So on to the next second question. Okay. So this, if everybody wants to take a photo, just to look back at it. Let me double check what this is from. I forget. Oh. So the first big thing is, what do you think we're going to use in the circuit? I'll read the question here a little bit. What do you think we're going to use? What y'all say? Main. I agree. What does main need again? Voltage sources, and what's the second part? Impedances. I agree. So what's something that the circuit has that's a problem for that? Yes.
that's a dependent current source.
Right, but it's still a current source. So that is our issue. Oh, network response functions. That's what this is called, I believe. This is from that sub part of y'all's problem set that says network response. Yes. So this is the second subtopic in your two problems. Okay. So I'll read the question for you. Okay. All right. The zero state RLC network shown in figure 88 was operating in the time domain where the network excitation is provided by an independent voltage source, E G of T. You are asked to do the following. Derive the numerical form of the S domain MAME using the clockwise orientation mesh current. So basically just use the arrows. What do you call it? You express MAME in the usual form of that. Apply Kramer's rule to the MAME to extract S domain equations shown in here. Remember or see that form that I was telling you about earlier? K times N of S D of S. Normalize the numerator and polynomials of YT of S with a coefficient of the highest power of S in each polynomial. This is what I was talking about. Earlier, I was saying we need to factor out. Normalize is the better way to put it. But yeah, so we'll essentially be doing the very similar math. So this one has a lot of components, so I'll probably skip the algebraic expression just for time's sake. But later on, if y'all want to do it yourself, just you can check with it. Okay, so like I said, we have a problem. We got a current source. I'm too lazy to read all the circuit, so I'm going to do this. Well, actually, what do we do with that? How do we get it to what we want, as in voltage sources? Okay, we have a current source with a what? In parallel. So then we have to do what to get a voltage source? Yes. But what do we have to multiply by? I agree. And that is because it is 1 over SC3 is the capacitors. I agree. All right. Oh, I forgot the capacitor. Of course I did. All right. All right. We're going to keep the same orientation to where plus is on the bottom. That's over here. This becomes SC3. So this becomes GM over SC3 times V2 minus V4. We agree? Yeah.
Wait, so just
Yes. Yes.
like a sort of
Exactly. And so remember in like circuits 1, you were doing source transformation with resistors and you used resistance, or you source transformed it with conductances and you used conductors. You get what I mean when I say that? It's the exact same thing, but we're using impedances and admittances. So we're using the impedance of that capacitor, which is 1 over SC. Since it's C3, we're going to label it C3.
Do we now have to figure out what?
No. What we're going to do for these type of problems, we do not need to find the voltage source numerically. We're going to do it symbolically. The only time you need to find, I think one of the only times we express sources numerically is like Thevenin's. I could be wrong, but that's really the only time that I've seen, at least in this problem, this review session. If my memory serves me correct, the only time we really have our sources numerically is Thevenin's and Norton's. So yeah, so appreciate the question, but yeah, we don't need to do it numerically. And also, if we don't have a numerical value for the source, you're not going to be able to find it. So if it's not numerical, don't expect to find a numerical. All right. So like we said, main. So the elements in mesh 1 is R1 plus SL1 plus 1 over SC3. We agree? Okay. What's being shared between 1 and 2? Yep. So that just becomes -1 over SC3, -1 over SC3. All right. And the things in the second mesh are 1 over SC3 plus SL4 plus R5. One other thing. I would be shocked if Russell gave you a circuit with this many components. He tries to get the components down for the tests. So it'll have like this circuit here. This is on my test. So like it's relatively simple. There's only 3 components and 2 sources. So it's not too bad. So this will then be IM1, IM2. And that equals, what's in IM1? And I'm going to have things in terms of EGs. What is the sources connected to IM1? And? Correct? And so would you agree that it is in mesh 1?
Yeah.
Okay. What is the polarity of that source? Positive or negative? I agree. Does everybody else agree? I'm going to erase this S. It's going to cause me to lose room. That's not supposed to be a V2. All right. What's in mesh 3? 2. There's only two meshes. Well, what are the sources in mesh 2? Yep. And, well, the source we just created, and then that dependent source. Now, the source we just created, is it going to be positive or negative? Now it's going to be negative, I agree. And what about the dependent source? Is it positive or negative? I agree. All right. So now I'm going to break up this matrix here. So we have EG 0 plus GM. Oh, actually, I'm going to do this first. I jumped the gun. What is our V2 in terms of mesh currents? And remember, we can't just get voltage from current, so we got to do something in between. V2, sorry, it's right here. Oh, wait, is it V2 that I'm looking for? Yeah, I'm going to do V2 first. V2 is right here. And the positive end is here. And the negative end is on the left. Right. Positive on the left, negative on the right. Correct, but is it positive or negative? Why are you saying it's negative? Correct. If we were to, when you think of current flowing from high to low, as in from positives and minus. So we have a positive on the right, negative on the left, going from high to low. So we have that sort, we have the arrow of our current, and it's going the same direction of our current. So I agree, it's positive. That becomes SL2 times, IM1. V4 is what? V4 is here in terms of mesh currents. Yep. Yeah. And then we also need V1. So what is V1? V1 is right there. Exactly. Just Ohm's law. Because we can't just get voltage from current, so we have to use that relationship of Ohm's law, V equals IR, or V equals Z. Technically, I just reversed that for some reason. Okay, that becomes R1. What did I say? IM1. So that then becomes GM over SC3 times V2 is SL2 times IM1 minus V4, which is R5 IM2. Okay, and so the same thing here, just negative SC3, SL1, is it 1 or 2? No, it's 2. Times IM1 minus R5 IM2. And then that is subtracted by a mu times V1, which we said was just R1 IM1. So then I need to break that up into the separate resistive matrix and our times our currents. So that means we have GM SL2 over SC3 for the top left, and then we have a negative GM R5 over SC3. Y'all agree? Times that IM1, IM2. Y'all agree? Cool. All right, and the same thing here, just negative, almost. And that is also being subtracted by an R1 times mu. And then the thing touching IM2 is a positive because it's a negative times a negative. GM R5 over SC3. Okay, why did I write 2 C's? SC3. Y'all agree? So now I just need to subtract this matrix over. So that then becomes a lot of terms. R1 plus SL1 plus 1 over SC3. Here, what am I doing? Minus GM SL2 over SC3. Next one is negative SL1 over SL3 plus GM R5 over SC3. Bottom left becomes -1 over SC3 plus GMSL2 over SC3 plus mu R1. And then the bottom left is 1 over SC3 plus SL4 plus R5 minus GM R5 over SC3. Holy crap, that's a lot. IM1, IM2, and that all equals EG. Do y'all agree? What's up? It's a lot of letters. So just to save time, I'm not going to go through the algebra. I'll do this real quick. So as given in the problem. Oh, by the way, we've done we've done number 1. This is part A. Done. I guess you could put numbers into it. Whatever. So in the question, it asks for this right here, IM2 over EG. So you simply put that in. All right. So y P of S equals I and 2 of S over EG of S. Well, what does IM2 equal? IM2 goes back to the whole Cramer's rule thing. We're looking for the current in 1 and our independent source. I'm sorry, we're looking for the current in IM2 and our reference is in mesh 1. So what are we going to be, what's going to be our exponents? Our reference is in 1 and our mesh is in 2. And we have that I plus J, where I is our reference and J is what the current we're looking for. That's the perfect guess. 1 plus 2. Why did you say that though? Exactly.
Then you said.
I said our mesh current's in 2. So we're looking for the current in mesh 2.
Why is there?
Well, it's, our reference point is what we're looking at from the source. Our reference point is whatever source is. Oh, independent source. Independent source. Because when I was going through this, I saw some stuff that was like delta 2, 2, and I'm like, why is that delta 2, 2? And I'm like, oh, there's a source in the second measured node. I forgot whose name or name. And we're looking for the voltage or the current that's connected to that mesh or node. So
We're never gonna have to worry about.
I don't think so. I don't think so. I could be wrong. I don't think so. I think good. I'm gonna be honest. I'm rough on that scenario. So this just makes sense to me. If that makes sense to you, go for it. If Cramer's rule, the algebraic way makes a lot of sense to you, go for it. But it should give you the same results. It should. Sounds great. Love to hear that stuff works. So, all right. So that's that. Delta 1, 2 over delta. And if we need mesh currents, technically, this whole thing here is kind of finding your inductance. This term here, the delta or the Cramer's rule part of your MAME, the Cramer's rule part of your MAME is finding your admittance. The Cramer's rule part of your name is finding your impedance. And I can prove that. So we have I equals Cramer's rule times EG of S. Well, if this is I times or equals something times voltage. Well, the only way that works is if this is conductance or is admittance, because if it was 1 over, it'd have to be impedance, and this is not 1 over. That make a little bit of sense? And I can also prove it further. This is all over EG of S. Boom, boom. I found my Y trans admittance. -1 negative delta 1, 2 over delta. That's what we're looking for. So, negative delta 1, 2, looking back at this, becomes a positive SC3, negative this term, negative that term. That then becomes, there we go, 1 over SC3 minus GM SL2 over SC3 minus mu R1. Wow. Okay. Do y'all agree? From this thing here, we got that thing multiplied by negative. I assume we agree. Okay. So from here, I am going to spare you the derivation because it's a lot. So I'm also going to put the numbers in there. You're going to be kind of like, what's going on? But I trust you, the fact that we did a bunch of the derivation in the next problem, and we will be doing it more later on, that you can do the process. So I would recommend working on whatever process works for you, and hopefully you get the same answers as myself. If you don't, come and talk to me at some point. I'll be available the next week because your test is literally next Wednesday, right? Yeah. Okay. So yeah, come talk to me. I'll be in the IEEE room for a lot. So yeah, if you have any questions on what I did in terms of derivation, just let me know. So I'll go to this form here. Okay, not that. Okay, so YT of S, when we do our derivation, have a fraction, I get these values. Negative 940 plus 10 times 10 to the 9th over S, all over 47 times 10 to the negative 12 S plus 940 times 10. That's supposed to be an S squared, sorry. Times 10 to the negative 6th here, plus 53 times 10 to the 3rd, minus 7.4 times 10 to the 12th over S. Well, notice we got an issue. Well, what is my issue? In terms of our terms, like our coefficients, we have numbers that have what in the denominator? Exactly, and that's problem. So therefore, I want to multiply by 1, or S over S. So that just becomes YT of S equals negative 940 S plus 10 times 10 to the 9th over 47 times 10 to the negative 12 S cubed plus 940 times 10 to the negative 6th S plus 53 times 10 to the negative 3rd S, this is supposed to be squared, minus 7.4 times 10 to the 12th. We are almost done. What is the one thing we have left to do? We have what, if you look at the polynomials, as in the things in our numerator and the things in our denominator, what does our highest form of S have? Highest form of S of, this is the lowest form, this is the next lowest, this is the next lowest, this is the highest. What does our highest form of S have attached to it? It's a number that's not 1. We have to then normalize the whole equations. Does that make
the
highest form? The highest. So you want to get it into this form of where your highest form's on the left and your lowest form's on the right. Does that make sense? And in this case, our highest form is an S cubed. It's not S squared, it's S cubed. So because of that, we need to factor or normalize these numbers. YT of S equals, oh, and you also want to make sure that the highest form of S is positive. So if you have a negative attached with that, take that out as well. Negative 940 over 47 times 10 to the 12th, negative 12th, I was right, negative 12, equals S plus, when you divide this number by this number, you get 10.638 times 10 to the 6th. All right, same thing here. S squared plus, nope, not an S squared. I'm used to that. S cubed. All right, and we divided this number by this number to get 20 times 10 to the 6th S squared plus, same thing there with that next term of 53. We got a 1.28 times 10, oh, I'm sorry. 1.128 times 10 to the 15th times s, and minus 157.447 times 10 to the 21. My handwriting is trailing off a little bit. So when we take this fraction, negative 20 10 to the 12th. Same thing though. Oh, no, I forgot some numbers. 10.638 times 10 to the 6th s cubed, sorry. 10 to the 6th s squared plus 1.128 times 10 to the 15th, all times s, minus 157.477 times 10 to the 21. All right. What do we do now? What were we looking for? I'll go back to the top of the problem real quick. What were we looking for in part B? Well, if you go even more right, we're looking for a k times n over d. Well, what do we have here? We have a k times an n over d. So we're done. That's it. Now, the process I showed you was much shorter because I didn't do the determinant derivation, but like I said, do it yourself, check it with this. I'm going to post this PDF in the Discord group chat, same place where the Circuits 2 stuff was. I believe that is UTA group. That's what it's called. Yeah. Any other questions on this problem? Process is similar as you saw. You see, we still had to do that. We got a fraction, right? We had to normalize that fraction, and we have a k and a times an n over a d. So it's a similar process. We just do it a little bit differently in the end. So, does that make sense? Cool. All right, on to the question. Oh, I didn't take it. Wow. I delete this page. Why not? All right. Is this where we get into? What do we get into? Okay. Open circuit, short circuit, natural frequencies. That's what this problem is. I'll read it. The scaled RLC network shown in figure 2 is operating in the zero state conditions where all initial conditions are zero. Identify and label the natural frequencies of the network with respect to open circuit and short circuit connections from A to B. Indicate the stability conditions for each connection. Be specific as to the connection for stability. So, first thing we do. What? What's the first thing we do? I thought somebody said it for a second. Okay. I like my arrows all going the same way. Just makes it easier on me. So I'm going to do that. So, are we good to start this problem? Do we have any issues with the circuit? No? Okay. I agree. I agree. This was literally last year's test. I mean, look at the numbers. Oh, I kind of blocked one. No, I didn't. We got a 1 Henry. By the way, these numbers are just purely imaginary. You will never see these numbers. Mostly never see these numbers. I mean, you might see, I feel like there's a 5 ohm resistor out there, but you're not going to see a 1 Henry inductor because that's crazy. What's up? It's crazy high because like I feel like a normal inductor range is somewhere between like the low millis to high like nanos, and the capacitor is crazy because I feel like the lowest capacitance I've seen is like 10 to the negative 12th, and the highest I've seen is realistically is like microfarads. So a 1 farad capacitor is crazy. You're not going to see that actually. This is just for simplistic computation. All right. So same old process for resistance. As y'all have seen, when I do name and name, I like to keep my variables is just variables. I don't like to put numbers in it. Y'all put numbers in it, perfectly fine. So what's shared between the two? R2, negative R2. So the thing between the three, or on mesh 2 is R2 plus R3 plus C4. Oh, next door, the dean of the school is having a luncheon, so I wanted to reserve that room, but we could not. I think it gets a little bit brighter. So then we do this. I am 1, IM2 equals our voltages, which in this case is this thing. Yes, yeah, it would be positive. Yep. I'm gonna delete this. Eg of S plus mu V1 plus V4. It's negative in the other one because it's flipped. V1 plus V4. All right. What is V1? Yes. Yes.
The C4.
You. Yes, it is. I was definitely testing it. All right. Pass. So okay. So what is V1 in terms of nodal voltages? Nope. Mesh currents, because we're using mesh. IM1, yes, in mesh current, but yeah, I agree. Yeah, it's flowing technically, like I said earlier, if you were to put the polarity of current on it, it's flowing from high to low, so therefore it's flowing with the direction. Literally, like on your problem, if you need to write the polarities of your current for these things, go for it. Like if that helps you, please do it. Because for a second, last night I was doing it and I was like, wait, does this go, is it positive or negative on this thing? And then I just drew the polarity of the like current. So the same thing there. And it helped me out tremendously because for V4, it's then the same thing of 1 over SC4 times IM2. And it's positive because the direction of the current's going the same way. Do y'all agree? All right, so same old, same old. EG, oh, that's kind of sucky. Okay. EG of S0 plus mu times SL1 IM1 plus 1 over SC4 IM2. This just becomes negative mu SL1 IM1 plus 1 over SC4 IM2. All right, now we move this matrix into 2. Mu SL1, mu over SC4, and this is literally the negative of it. All right. All right, so when you add these together, I'm sorry, when you, I guess, subtract these together, you get R2 plus SL, SL1 minus mu SL1. This then becomes a negative R2 minus mu over SC4. This then becomes R2 plus mu SL1. And this side becomes R2 plus R3 plus 1 over SC4 plus mu over SC4. I like to keep all my components separate. Yes, I could probably scale these down in terms of combined like terms here and combined like terms here, but I don't want to. For me, I literally tried it with that yesterday and it wasn't working for me. So then I did this again, worked just fine. So everybody's got their own way of doing things. Doesn't matter if it takes slower or longer, or slower or shorter. It just matters just get it done and get it done right. All right. EG of S, right? Yep. 0. All right. So we're looking for the open circuit and short circuit natural frequencies in connection AB. Where is connection AB? Which is in, exactly. So we do the same thing again. What's our I and J if we're looking for the current in mesh 1 and our references in mesh 1? Exactly. Does that make sense? Got a question?
Say yeah. Take time.
No, we got time. We got a lot of time.
Well, like when I was doing my thing, I've been like,
Oh, I got you. So No, no, you're good, you're good. We're looking for the current in mesh one. Okay. Yeah. So we're looking for the current. The reason I'm saying we're looking for the current in mesh one is because we're looking for the short circuit, open circuit natural frequencies connected to terminals A and B, and that is in mesh one. So we want to look for the current going through that mesh one. But we also have an independent source in mesh one. Okay. So our reference is our mesh one. Our reference is our independent source in mesh one, and what we're looking for is our current in mesh one, and that is why we do exactly, because this is our reference where it is, and this is what we're looking for where it is, and they're both in mesh one, so they're both one. So, yep. All right. Delta 1, 1. So that's first row, first column. That's left. Does that make sense? Delta 1 or row 1, column 1, whatever's left. That's what you get. That then becomes R2 plus R3 plus 1 over SC4 plus mu over SC4. I am going to spare you the derivation because I don't want to do that. So also, we have, right, we have this equation here. Why did I say? Yeah, we have this equation here, which equals IM1. Another thing with short circuit and open circuit natural frequencies, you're going to either want to find your driving point impedance or your driving point admittance. Yes? No? That makes sense? Russell's talked about that, I assume, because he talked about it when I took it. So we have we have a current times Kramer's. I'm sorry, we have a current equals Kramer's times a voltage. So if we want to get either impedance or admittance, we want to divide by this voltage. Well, what do we get when we divide current by voltage, as in I over V? Admittance or impedance? So a V equals I R, and we have I over V, what would it equal from this? 1 over R, I agree, which equals yes, 1 over R. So I over V equals, I'm just going to call it Y. So we are finding our driving point impedance. And that is important. That is very important because it kind of tells you where your open circuit and short circuit natural frequencies are.
Impedance or admittance? Driving point.
You can find either.
Oh, okay.
But what I'm saying is your MAME finds your driving point impedance, admittance. I'm sorry. Let me rewrite that. And NAME finds your driving point impedance. Because when you do the derivation, as you're shown here, you'll find it to where I equals something times E or V, divide them over, you get driving point impedance, admittance, driving point admittance. And if you were to flip that to where your E or your V equals something times I, V over I equals impedance. Driving point admittance. Okay. So I am going to we're going to start here. R2 plus R3 plus 1 over SC4 plus mu over SC4. Like I said, I'm not going to do the derivation of the determinant. You do that on your own and make sure that it matches. So R2 plus R times R3, R2 over SC4 plus SL1 R2 plus SL1 R3 plus SL1 times SC over SC4 minus mu SL1 R3. All right. What's our issue? What's our issue? Bingo. Exactly. So, I want to divide by 1. I mean, multiply by 1, sorry, which is Well, I want to get rid of also just C4 in the new denominator, just make it easy. So I just have nothing in denominators. So I'm gonna now I'm gonna combine like terms. That's just how I liked it. SC4 times R2 plus R3 plus 1 plus mu all over. I'm going to skip to where I have combined like terms. S squared L1C4 times R2 plus R3 minus mu R3 plus S. That's a really bad R3. Plus S times C4 R2 R3 plus L1 and all being added by R2. So the steps I skipped was I multiplied that and that out. And I just simply rearranged this whole polynomial to where I have all my S squareds together, S's in terms with no S's. Those are the only steps I missed. So I'm going to put some numbers in here. So when you put your numbers of almost all of them are 1 besides R2. I think R2 is 5. Just double check that. Yeah, literally everything is 1 besides R2. Oh, and mu. Mu is 7. That's important. When I do that, it then becomes S times 6 plus 8 over S squared times a negative 1 plus S times the 6 plus 5. All right, what do we do now? We have polynomials where we have highest forms of S's, but they're being multiplied by something that's not just 1. So therefore, we need to normalize our polynomials. So up top, we have a 6. And remember, we also want a highest form of S to be positive. So then we have a negative 1 that we're going to pull out. So it becomes S plus 8 over 6 all over S squared minus 6S plus, nope, not plus, minus 5. My 5 looks like an S. That still looks like an S. All right. Does everybody see how I did that? Does anybody have any questions about how I did that? Let me know. Okay, nah. If I were to multiply these terms, and like I said, I had to normalize it to where our highest form of S just is multiplied by 1, a positive 1. So I had a 6S and I had an S squared to the negative 1. On both sides, or on the numerator and the denominator, I took all that out. So the S is, or the 6 is over here, and the S is here, and we have an 8 times 6. Well, if we were to multiply this 6 times S plus 8 over 6, we'd get 6S plus 8. So these are equivalent. Does that make sense? Same thing with that bottom one. But that's just a form that we want to do because we want to get it into that K in D. We want to always get it into that form. And our K in this case is negative 6. Okay. So the next thing we need to do is we need to find the roots of our polynomials. That is how you find what your natural frequencies are for this scenario. Does that make sense? When you have your driving point impedance or admittance, you need to find the roots of your polynomials. Does everybody know how to do that? You got a calculator in. Well, I'm not using quadratic form. That's too much time. How do you find that on your calculator?
We do not. Well, hold on, wait. You're saying that we can find the root automatically with a number?
Yeah. Yep. So, does everybody have access to a TI Inspire? Okay. Cool. It's the best freaking friend. Best friend. Well, you're about to learn. So, I'll wait till everybody gets that out real quick and then I'll show you how to get to it. So, it's menu. Where is it again? Wait, how did I do it earlier? Sorry, give me 1 second. My brain is not working on full. I did a lot of calculations yesterday. Oh, okay. Go to menu, go to algebra, Go to factor. So those numbers are menu 2, nope, menu 3, 2. Menu 3, 2. So literally type in s squared minus 6, and you have to put in times s, 6 times s, minus 5, and you have to tell it what number to factor. So you have to hit a comma s. And you should get this. The numerator, it's simply just saying, what do you call it? Just do 8/6, and you'll get the value of 1.333 repeating. But when you take the roots of those, you'll get an s minus 6.741, close parentheses, and a s plus 0.741. Did y'all get the same thing? Okay. So our zeros in this case, our numerator is 1.33. Our denominator is 6.7 and negative 0.741. Did you get it? Cool. Does everybody understand what I mean by that? As in the zeros are just the opposite of this sign. It's your zeros or whatever you would plug into S to then get 0. Does that make sense? So you would plug in a positive 1.333 to just get 0 in the numerator. You'd plug in a positive 6.7 whatever to then get 0, and you put in a negative to get 0 here. Does that make sense? Because you're finding the 0 of that function. There are 3 roots. 1 is in the numerator and 2 in the denominator. That's a better way to say it, because if you say 3 roots, they're going to be like, well, where? Numerator, denominator, blah, blah, blah. And it matters for here. Okay. So where's your short circuit? Where's your open circuit? Because we need to find our short circuit natural frequencies and our open circuit natural frequencies. Here is how I find, this is how I remember it. Okay. So let me go to let me go to impedance. Okay. Impedance is V over I. Are we in agreement? Okay. V over I. So when you have a short circuit, what is the value of your impedance? You have a short circuit. What is the value of your impedance? 0. Okay. So that means for a fraction to have 0, would you need a 0 in the denominator or the 0 in the numerator? I'm sorry. Well, yeah, I said that right. Just flip. Exactly. So when you have a short circuit, that means you have a 0 in the numerator, which means your numerator will have your short circuit if it was driving point impedance. Give me 1 sec, because we're using a driving point admittance for this problem. So also for driving point admittance, I'm sorry, for impedance, you have an open circuit. What is the value of impedance for an open circuit? Infinity. Where on a fraction, if you put a 0, would your number then be infinity? So if you put a 0 on the numerator, we said it's going to be 0. Put it on the denominator, your number becomes infinite. So if you have a 0 in the denominator, you then have an open circuit natural frequency. Does that make sense? Kind of makes sense? Well, what's admittance? The opposite. Simple as that. That is how I like to describe it. Did that kind of help? I've told a couple people that in the past, and it's really helped them. This is how I like to think of it. I think this is really helpful. Short circuit, 0 voltage or 0 impedance. Open circuit, infinite impedance. So that's where that goes. Admittance is literally just the opposite of that. So what is our numerator in this case? Is it our short circuit or is it open circuit natural frequency? The fact that we're using driving point admittance. Is it short circuit or open circuit? Our numerator. Open circuit, exactly. Your open circuit omega n equals 1.333 rads per second. So if our numerator has our open, then our denominator has to have our short. It's rad per second. Oh, why am I doing that? Okay. Is this making sense? Is this making sense? All right. We're not fully done. So we need to also be specific to the conditions for stability, as in we need to indicate the stability condition for each connection. Okay. And when he says each connection, he's talking about either the open circuit connection or short circuit connection. So earlier I talked about a class called control systems. Circuits 2 uses the theory of control systems. Okay, so it's another class that you can take. Professor's really good if you really want to take it. It's going to be similar math, but not as in-depth, not as freaking difficult. There's not as many variables. And you're not only going to think of it as circuits, you're going to think of it as actual like feedback loops and stuff. So to find out whether a system is stable or unstable, you need to look at the poles of a fraction. Do any of y'all know what I mean when I say the poles of a fraction? What do I mean? I agree there, yes, but when I have a fraction, where would I find my poles? Exactly, the denominator. The poles, when I'm saying poles, I'm referring to a term that Russell has also used in terms of holes and poles. When you have this number here, right? Okay. If I were to put this on the graph, okay, my numerator is where the graph is going to be equal 0. So there's a big hole. Okay. So let's see 0 or I'm sorry, positive. Give me 1 second. Why did it? I'm an idiot. These are different. This is different. Okay, that makes more sense. Okay, I had the numbers flipped. I'm sorry, I had the signs flipped. That's my bad. Okay, so this makes sense though. So this, if I were to find the 0 of this equation, it'd be over here, right? Be like, let's say right there, it's a 0. Okay. A pole is when your function goes to infinity. So when your function goes to infinity, you got zeros in the denominator. Why it's called a pole, because it literally looks like a giant pole. So like, let's just say that's -6, and let's say this is positive 0.7. Okay, so I have a hole and I have a pole. Okay, so you want to look for the short circuit poles and you want to look for the open circuit poles. So we have the driving point admittance, which in the denominator has our short circuit poles. Does that make sense? Because we're looking at the denominator of our driving point admittance, and we've already defined that as our short circuit omega n. That, do y'all agree? Yes, no? Y'all got any questions on that? Okay, I'm going to trust that you understood that. So another thing with stability is we have to look to where those poles are. This is technically called an S-plane. It's also, you can just look at it as the real on the X, imaginary on the Y. It's just the S-plane. Yeah. Okay. So if we were to find this number here, like I say, the short circuit natural frequency has the whole, I'm sorry, the short circuit natural frequency as in the S plus 133, as in -0 of that is -133. 1.33. We agree with that? As in we said that here a second ago. Y'all agree with that? I'm saying stuff backwards. The open circuit the open circuit natural frequency is 1.33. You agree with me on that? Because we found that a second ago. I need to change these frickin' things. There we go. The open circuit natural frequency is negative 1.33, as we found here. It's just the zero of this this number here. Okay. So it is negative, which means it's going to be in the left half. It's going to be in this half here because it is negative. You agree with me there? It's going to be the negative of the plane. Okay. Stability is found by if your poles are on the left half of the open left half plane, as in it's on the left half of the graph in respect to the origin. So this number is on the left half of the graph. There's only one number and it's only on the left. So it's going to be stable. It's going to be stable. Okay. Now your short circuit natural frequencies, you have a number that's negative, you have a number that's positive. What does that mean? We have a number that's negative, so that means it's going to be on the left. We have a number that's positive, which means it's going to be on the right. You have one number that is not on the left half plane. Therefore, unstable. So, like I said on poles, we have the admittance. So our poles are the short circuit natural frequencies, as in here. So we looked at the poles. If you want to find the open circuit poles, you literally just flip it, or you can just look at where the numerator is and say it's either going to be on the left or the right. So, because of this, open circuit condition stable, short circuit condition unstable. Do y'all agree based on my saying? Your open circuit 0 is on the left, so therefore your open circuit condition is going to be stable. Your short circuit conditions, one's on the left, one's on the right. And since one is on the right, that literally just means it's unstable. Literally anything on the right, unstable. It's just unstable immediately. That makes sense? Yes. Okay. You're good. We will eventually find our driving point admittance or impedance. Here we found our driving point admittance. Therefore, we have to find that as open circuit natural frequencies are in the numerator and short circuit natural frequencies are in the denominator. You with me on that? Okay. And if you want to find out if it's stable or not, you literally just want to find the root of that function. You want to find out if it's in the left or the right half of your S-plane, where your S-plane is literally just defined as this. It's just it's a real and imaginary graph. You with me so far? So when we looked at our open circuit natural frequency, the root of that becomes a negative number. Okay. And so it's a negative number. It's going to be on the left. You agree with me there? So because of that, because it's negative, and it's because it's on the left, and when it's on the left, and only on the left, it is stable. So everything in your open circuit natural frequencies is on the left. Therefore, your open circuit natural frequency conditions are stable. So the short circuit, if you look at it, we have a number that's negative, we have a number that's positive, we have a number that's on the right, unstable immediately. Does that make sense? Sweet. All right. Any other questions on this question? Cool. Well, I'm moving on to Thevenin's. Thevenin's. Good old Thevenin's. Okay. What does Thevenin's use? Name. And? Since we're using name in terms of resistance or conductance, we are using. Bingo. Okay. So, just gonna jump into it. Y'all, anybody want to take a photo? Probably should ask that before I start. I'm gonna take a drink of water. Talking for a couple hours is interesting. This was actually also my test. Does anybody else want to take a photo? So, I'm gonna read it out. The conductive network shown in Figure 3A is an equivalent circuit of an NMOS source follower. It's just a type of circuit We don't need to get into that. The amplifier is driven by a 120 microamp current source. Obtain the Thevenin's equivalent at the terminals A and B of the network shown in figure 3B. Express E Thevenin's and R Thevenin's in numerical form. Show all your work, blah, blah, blah. What is the one thing we need to do for Thevenin's?
Identify the nodes.
I could say that. I was looking for something else. We have current sources, but do you think we have enough current sources?
No, we don't. We have to make one for them. Don't we?
We have to make an arbitrary source, and therefore, since it said name, we're going to make it a current source. Okay. What's the direction of current? Kind of anything we want, but also there's a polarity. I would recommend sticking with that polarity. So therefore, and I'm just going to title it J0. I'm just going to say, hey, 1 amp. All right. Time for some math. I hate the fact that these are all G's and they're not numbered. They're all just numerical G's, pissing me off. But we're going to do it. Okay. So G plus GF. Okay. So as you said, identify our nodes. Luckily for us, it's given. Node 1's here. Node 2 is here. Node 3 is here. And they might not be given, but if it's this complicated, they're going to be given. I would be shocked if this circuit did not, like a circuit like this was not given the nodes. Because it's kind of hard to give it, but it's also not explicitly hard. Because if you were to, what's up? Gonna be 3. I mean, so if you do the thing we were talking about, you kind of look at the top of it. Well, you go from here to here, you already ran into a component. So you got one node, but you got a component that breaks that node. So then you need to go reference it again, and you have a node again. You have a node here. Well, you have a breakpoint also from here to ground. Okay, if you're following it here, you're going down, but you also have a component here. You have a component between here and here. So if you're going down, oh, I broke my node. Now I have to have a third node. Done. All right. So we have determined that GG and GF are in node 1. What's being shared between node 1 and node 2 is GF. And between node 3 and node 2 is what? Is there anything being shared between node 1 and 2? 2 and 3. 2 and 3.
Yeah.
What?
No, I'm sorry.
I agree with that second part. So 0, negative GF, 0. Do y'all understand why I'm doing the same thing here? Isn't it the same numbers? All right. So the things being touch node 2 is GF, GD. What's being shared between 2 and 3? Nothing. Oh, wait, I probably won't do this. Very nice when I have my cheat sheet over there. And what's touching node 3? Just GS. This is VN1, VN2, VN3. That's a 2. It's a really bad 2, whatever. Things touching node 1, JG. It's going into. And there's nothing else. Node 2, we have 2 sources going out of node 2. What does that mean? I agree. Negative GFS times VG of S minus GMB VB of S. And for node 3, it's just flipped. GFS VGS plus GMB VBS. All right. Oh, I forgot something. What did I forget? For node 3, what did I forget? Yep, and it's plus. All right, now I'm going to break these down into the few different vectors and matrices. J0, boom, boom, plus 0, 0, J0. That's really bad. There we go. Oh, wait, I'll do this again. Why not? All right. We have 2 terms, VGS, VBS. Okay. We're looking at VGS. We want to turn VGS into nodal voltages. What is it? This actually stumped me on my test, but after looking at it in hindsight, I was 20/20, but. VGS in terms of nodal voltages, it is touching. I disagree. Now, I'm just trying to find this in terms of nodal voltages. If I was trying to find the voltage from positive to negative, I agree. But yeah, so it's touching two parts, right? We have a positive end touching node 1, and we have a negative end touching node 3. So if we have a positive node 1, negative node 3, what do we have? Yep, that's that easy. Yeah, I was stumped with that too in my homework, on my test, because I didn't realize, oh, we just need to talk about the nodal voltages and not just the voltage from that point to that point. Yeah, what's up?
You don't have to like use any of the spots in between them.
Because you, not in this case. So I think you're talking about that one problem we were working on. So that problem, you had a voltage and trying to think about what it was. It's not as complicated there. I believe, I want to say it also was, but it was dealing with mesh currents because it wasn't named. We had to find. Yes, because it was mesh, it was named. So we had to find a voltage from a current. So we had to multiply by that resistance or whatever.
Okay.
So we found the voltage in that area, but we had to then make that into the mesh current. And so we just took the current times the resistance or impedance, I'm sorry, plus the voltage there equals that. So it's the voltage of the loop, but we just wanted to make it equal to that mesh current. We had to find the mesh current. But since we have a voltage and we're wanting to transform it into nodal voltages, you just see what it's touching. So that tripped me up too on my first test. So yeah. I didn't even finish this problem on my first test. And VBS is right here. There's a negative touching VN3 and there's a positive touching ground. So that means Does everybody understand why it's negative VN3? We have a negative touching VN3 and a positive touching ground. And if ground is our 0, that's like saying 0 minus VN3, which is just VN3. Does that make sense? Cool. All right, negative VN3. So that means this is negative GFS VN1 minus VN3 minus GMB times a negative VN3. Right, yes. GFS VN1 VN3 plus a GMB times negative VN3. All right, now we're going to break that up into the nodal voltages. So, yep. So this just becomes negative GFS 0, oh, no. 0 because nothing's touching VN2. This becomes then just positive GFS because it's touching that and also GMB. Does that make sense for that? IM1, IM2, and there's nothing going on. I'm tripping. This is supposed to be 0. That is supposed to be there. There we go. That means that is negative GFS, and this is positive GFS, and that's positive GMB. Well, that could be bad. 0, 0, and it's literally just the direct opposite. GFS, negative GFS, that's 0 minus GMB. Does everybody agree? All right, so when we combine the thingamabobbers, we get. Did I say that? You're right. Thanks. I've done a lot of MAME, so my mind's on. It'll end by 2. The rest of it could be found on the recording of the HKN teams that have linked in the Discord. Perfectly fine. So, I'll probably be here. Okay, so yeah, when you add it, when you subtract over that matrix, you get this: JG plus JF, negative J GF. I said JF for some reason. 0 right there. Negative GF plus GFS, GF plus GD, negative GFS minus GMB, negative GFS 0, G. Is that S? Yeah, that is GS. GS plus GFS plus GMB times our nodal voltages. I'm going to write name again. VN1, VN2, VN3 equals J's G00 plus 00J0. We good? Cool. I'm just going to put in the numbers. When you put in the values for these terms, you get 55 micro, negative 5 micro, 0, 245 micro, 80 micro, negative 350 micro, 250 micro, 0, then 470 micro. This is all times VN1, VN2, VN3 equals our JG of 120 micro 00 plus 001. Do we agree? Okay. The first thing we're going to do is we're going to find E Thevenins. So what do we do to find our E Thevenins? I agree. Okay. Where is our E Thevenins? So E Thevenins, it is between the nodes that we place our source. Correct. Correct. And we're getting a voltage from a voltage. That's fine. So this matrix, you literally, when you type it in your calculator, you're going to want to do this. You're going to want to put that matrix, it's the -1, times your 120 micro, 0, 0, equals your VN1, VN2, VN3. If you do it the opposite, as in you do this, the JG matrix or vector times this vector, you're going to get like a domain arrow. So do it like this in your calculator. So where you have this 3x3 matrix to the -1 times that current matrix. Yeah, you can do that. I've never known how to do that. This is how I've done it every single time. If that works for you and you know how to do it, go for it. That's how I do this. But that you have a different way. But does this make sense though? If you literally, because you can't divide matrices in your calculator, but you can multiply it by the -1, which is the same as dividing it. So when you do that, VN1, VN2, VN3 equals 2.045, negative 1.504, and 1.088 volts. So what does our E Thevenins equal? If we set it equals VN3. What does E Thevenins equal if we set it equals to VN3? Exactly. All right. We also need to find our R. How do we do that? Say that one more time. Or JG, turn it off, yep, and turn on. Yep. And it's also still that V in 3, and it's divided by our J0. And that is where our JZ equals 0, JG equals 0. All right. So when doing that, as in have this exact same matrix, that this now becomes 0 and this becomes 1, get these values. 793.201. 8.2, nope, 8.725K and 2.549K. And that is technically volts, but since we're dividing it by that 0, our Thevenin's is that 2.549 divided by 1, K ohms divided by amp. Nope, that's not amps. That's or that's not ohms, that's volts. That means our Thevenin's equals 2.5549 K ohms. So I'm saying 9. So when you connect these, you connect it like it's shown in the thing. You got a resistor. You got a voltage source. E Thevenin's equals 1.3 volts, and R Thevenin's equals 2.549K. Simple enough? Do y'all want me to do a Norton's, or is it kind of just straightforward because it's kind of the opposite of that? Okay. I have one more problem after this as well. But
I just wanted to.
I don't agree with that right now, and I'll let you know here. Yeah. All right. So would y'all like me to go ahead and do the Nortons, or would you like me to go ahead and skip it? I literally don't care. Skip it. Cool. I kind of figured it was gonna be like that. It's just more MAME. Yeah. If y'all like to take a photo and do that problem by yourself, you're more than welcome to. Y'all, what is it? Come to me at some point if you want to know what the answers are to these. See if you got them right. So, all right. Last problem is an oscillator problem. So y'all literally just finished this up, right? For the lecture, not the actual homework, but you'll finish the lecture. So I'll read the problem. The schematic of an RLC network shown containing a voltage-controlled voltage source and a current-controlled current source is shown in Figure 1. Calculate the value of the voltage-controlled voltage source gain parameter mu in volts per volt, and the value of your current-controlled current-controlled voltage source transresistance, Rm in ohms. That will cause the sustained oscillation at frequency FO, I don't know why, of 175 kilohertz. I'm sure all your work can explain in detail. So what's step 1? Exactly. I've just been doing a lot of MAME. All the problems I've found is just a bunch of MAME. So, but if anybody needs any clarification on any name things, let me know. I've had plenty of problems that have done name. All right, so I like this direction always, so I'm gonna do this again. Okay. So yeah, okay, I'm gonna do MAME. So R1 plus SL2 minus SL2 minus SL2 was this was also my test. It's as in when I took it in my semester, this was the test problem on my semester. So the variables, they're not horrible. Not horrible. Negative SL2. So the things that are being used in mesh 2 are SL2 plus SL3 plus R4. IM1, IM2. Okay, wrong way. And that is equal to mu V2 of S, right? Mu V2 of S. And over here, RMI1 of S. All right. What does V2 equal? What does V2 equal in terms of this circuit? I think I was still writing. 31. In terms of mesh currents, what does V2 equal? I agree with that. I'm just gonna work it around a little differently. SL2 times IM1 minus IM2. And then also we need to find I1 of S, which that equals what? In terms of mesh currents. And I1 is up here. Right. What does that equal? In terms of mesh currents, what does I1 equal? Okay. M1. And it's just dependent sources. So we only have a dependent source matrix. That becomes mu times, I'll do that. SL2, IM1 minus IM2. And on the bottom becomes RM, IM1. Okay, do that. This becomes mu SL2 minus mu SL2 mu SL2 RM and 0. Do we agree? You all agree? Wait. All right. So when I subtract that matrix over, I get an R1 plus SL1, not SL1, SL2. SL2 minus a mu SL2. And over here I get my minus SL2 plus mu SL2. Now this then becomes negative SL2 minus RM. This becomes SL2 plus SL3 plus R4. All times IM1, IM2 equals 0 and 0. All right. So for oscillators, what do we need to find? I'll let y'all write it out here for a second, but what is the part of this matrix that we need to use? Determinant. I agree. So we're going to be doing this element times this element minus this element times that element. Simple matrix math. Define the determinant. I'm going to actually just go ahead and do the derivation. We got plenty of time, and yeah. Or if y'all like me to skip it, let me know. Delta equals R1 plus SL2 minus mu SL2 times SL2 plus SL3 plus R4, all minus negative SL2 plus mu SL2 times negative SL2 minus RM. All right. You want me to just go ahead and do the algebra? You want me to just go ahead and do it? I'll go ahead and do it. Maybe it is, whatever. Okay. Delta of S. Probably should have wrote that too. Okay, I'm doing that times that. So SL2 R1 plus SL3 R1 plus R1 R4. Okay, now I'm going to do that to that. Plus S squared L2 squared plus S squared L2 L3 plus S L2 R4. Okay, now I'm doing this to that. Negative mu S squared L2 squared. Negative mu S squared L2 L3. Negative mu SL2 R4. So I'm going to negative mu SL2 R4. That's that half. Now you go on the next half. Negative SL2 times negative SL2. This becomes SL2 squared. That to that becomes, is that supposed to be a negative R? Negative R. Oh, okay, cool. Okay, cool. So that becomes positive mu SL2 RM. And then going from here to here, I got negative mu S squared L2 squared. Then I have a negative wait. That mu is not supposed to be there. There we go. Mu SL2 RM. There we go. Does anybody agree? A lot of derivation, but okay. I don't want to pay for that. Let me just double check myself. Okay, cool. So now I can also cross out like term. Boom, boom. And SL2RM, I feel like I have that somewhere. I don't. I have this somewhere though. Yes. Yes. That's it. So our delta S, I'm gonna write this a little bit closer. SL2R1 plus SL3R1 plus R1R4 plus S squared L2L3 plus SL2R4 minus mu S squared L2L3 minus mu SL2R4. And then negative times a positive becomes a negative SL2RM plus mu SL2RM. All right. I'm going to combine like terms again into my S squareds, S's, and R stuff without S. Do y'all understand why I'm doing that? Cool. Is this the stuff that's fresh on your mind since you'll probably finished it literally today, I think you said? Delta S, this becomes S squared L2 L3 minus mu L2 L3 plus an S L2 R1 plus L3 R1 plus L2 R4 minus mu L2 R4. Oh, wow. Okay. R4 minus an L2 RM plus a mu L2 RM. And I'm going to shrink that a little bit, over a little bit. There we go. There we go. Yep. That is all being added by R1, R4. So, what do I do now? What would y'all recommend I do now? Exactly. So an S squared, if you put a J omega, square it, becomes just negative omega. So that equals negative omega squared times L2, L3 minus mu L2, L3 plus S L2 R1 plus L3 R1 plus L2 R4 minus mu L2 R4. Yep. Minus L2 RM plus mu L2 RM. Oh, this S, probably need to change that to just J omega. Yep. This is all being plussed by R1, R4. Okay, so what I like to do in this scenario, right? We have two parts of this equation. We have a real and we have an imaginary. Do y'all agree? Okay. So I like to look at those, a real and the imaginary parts, and figure out what is in what. Okay. So let's look at the real. So in terms of what we need to find mu and we need to find RM. So if we look in the real parts, I only see mu. If I look in the imaginary parts, I see a mu and I see RM. So what do you think we should do first? If we have a term with only mu, as in the real, as in the real, and we have a term with mu and RM, what should we do first? Do what? Yep. So since we have a part that only has mu, I'm going to use that first. Oh, also, we need to set these entire determinant equal to 0. That is very important. That is very important. So I'm going to take the real part. Negative omega squared L2 L3 minus mu L2 L3 plus R1 R4. Okay. Just going to skip doing the math. I'm sorry, not doing the math, but doing the derivation to find mu. But I'm going to tell you how I got from here to then mu. Mu equals 1 minus R1 R4 over omega squared L2 L3. Okay, so I just basically subtracted this over here, factored out the mu, factored out the L2 L3, then divided that by this, whatever, and I got here. So I would encourage you to try to get from here to here on your own, and hopefully get the same thing. I have checked this, and I know it is correct. So when you plug in the values for everything, and you're given F naught, but your equation has omega. How do you get omega from F naught? Omega, yes, from F naught to omega. I disagree. Omega equals blank and F naught. Okay, so sorry if I said the opposite. Yeah, I need to get omega from F naught. I multiply by 2 pi. So just omega equals 2 pi times 175k. When you do that, when you plug in all the values, you get an omega of negative 826, sorry, 0.112. And we said the units earlier given in the problem statement is volts per volt. Okay. So now we have that. Now we plug it into our imaginary. And remember, when you take the imaginary, you don't need to take the J. You already have. You're telling it that you're taking the imaginary. So I am of delta J omega equals omega times L2 R1 plus L3 R1 plus L2 R4 minus mu L2 Rm minus L2 Rm plus mu L2. Oh, this is not supposed to be Rm. This is supposed to be R4. Yes, it's R4. R4, sorry. And Rm's over there. That's all equal to 0. I'll spare you the derivation, but when I finished up, okay. This lock is not locked. When I did the derivation, I found that Rm equals L2 times R1 plus R4 minus mu R4 plus L3 R1 all over L2 1 minus mu. Now you can derive that equation in any other way, just as long as you get an Rn of 2.001 K ohms. So I encourage you to move that or manipulate that equation, however way y'all usually do it, and hopefully get the same answer, because that is the correct answer. All right. Well, that's all I got for you. Any questions currently of the review? Yeah. Cool. Well, I will then stop the recording. Oh, that's the wrong thing. I'll stop the recording. Oh, wrong thing again. And you can find this on, like I said, the HKN Teams channel or Teams team. I linked that in the UTA Discord, the UTA EE group Discord. So, yeah, I'm gonna stop the recording and yeah. There we go. And, what the heck is, there we go, stop recording. All right.